Hi, I'm Adam Landos. I'm here to talk to you about how topology is applied in modern solid-state physics, and I'm going to talk about topological materials in general. Okay. So, first of all, why study topological materials? First of all, this is a huge field that has been booming for the past 10 years, and it has been from revolution to revolution. And it has many interesting characteristics, like it provides us with dissipationless currents that transport charge or spin, and they are very robust against disorders because they are so-called topologically protected for the reasons that we're going to see in a few minutes. They provide us with the first realization of Weyl fermions in physics. They also give us high energy physics effects and relativistic physics in materials. They have wide applications like in quantum computing and high performance electronics, and especially spintronics, among many others. So let's delve into it then. I'm going to talk to you just a bit about general band theory. If we have a single atom, we know from the quantum theory that we in general have discrete energy levels, as we see here. But if we put an Avogadro number of them together to form a crystalline solid, then we in general have many different bands that are separated by gaps, possibly. And within each band we have a continuum of states labeled by a continuous parameter, which is the crystal momentum K. This is a K-space. Now I'm going to tell you about the integer quantum Hall effect, where if we take a 2D sample and put it in a perpendicular magnetic field, in the bulk of this material we will have the particles that will complete Lorentz orbits, and this corresponds in the quantum theory to localized states. But in the edges of the material something strange happens, or interesting. The particles try to complete their Lorentz orbits but hit the boundaries and then get into the next Lorentz orbit. And this happens again and again to the point that they start moving along the boundaries. So in the quantum theory, these are the extended states, and we expect them to contribute to the Hall conductivity. In 1982, Thouless, along with his collaborators, tried to solve this problem using only the quantum mechanical theory, and they found this expression here, where here they integrate over a quantity that is of interest to us, which is of deep geometrical origin, and we'll see it very shortly. But the important bit here is that this is proportional to an integer n, which it was called the TKNN invariant, and it has a topological origin which protects the Hall conductivity here. Here we can see a typical graph of the Hall resistivity, where we can very clearly see the jumps in the resistivity here. For this work, among others, Thouless received half of the 2016 Physics Nobel Prize for his work on topological matter. Now, I'm going to talk to you about a very fundamental topic in quantum physics that was discovered about 65 years after they thought they had completed the theory of quantum mechanics, and it's various phase. But let's motivate it first geometrically. If we have a vector and we want to transport it by keeping it parallel to itself, and we want to transport it along A, B, C, and then A again. If we have a plane, like a flat space, and we do that, then of course we can keep the vector as it was in the beginning without rotating. But if we try to do the same on, say, a sphere, for example, which is curved, if we go from A to B, and then take this vector and get it to C, and then way back to A, then the final vector rotates with respect to the first vector. And it turns out that this is also true in the quantum theory, where if we have a state n, at an initial state n, then it picks up this non-trivial phase factor here that has to do with that rotation that I told you about. And that gamma n there is the Berry's phase, which is defined with respect to the so-called Berry curvature, which is in turn defined in this way with a quantity that I'm not going to give here. And it's like a magnetic field in the space of parameters. I forgot to tell you that this transport here of the state, for example, on a sphere, happens in a parameter space. So for any problem, we have some parameters that we can tune, like in experiments, for example, and this transport happens in that space. So essentially what this tells us is that the Berry phase, essentially the flux of this quantity here, the Berry curvature, through the surface that has as a boundary the path in parameter space that we are taking. As an example of the Berry's phase, we will consider the Aharonov-Bohm effect, where if we have a particle in real space that goes through a closed path that encloses a magnetic flux, if we have a magnetic field there, its state acquires a non-trivial phase factor, the Aharonov-Bohm phase factor. But if we take the parameter space to be the real space in our case, then the Berry curvature is indeed the magnetic field, and then the Berry's phase is actually the Aharonov-Bohm phase. Now the most important bit about all this baryological physics is the Chern number. If we take a closed manifold and we find the flux of the Berry curvature through it, and divide by 2 pi, this gives us an integer. And this relation here is a generalization of the Gauss-Bonnet theorem from mathematics, which is very famous for mathematicians. And this C here is an integer, and it's called the Chern number. And it's actually a topological invariant in the following sense. If, for example, we have a sphere and we smoothly deform it without ripping it or doing anything rough to it, then we get a shape like this. But these two are topologically the same, and they have the same Chern number. But if, for example, we poke a hole in any of these and get, for example, a donut, then the Chern number changes, and this is topologically distinct from these two. So now I'm going to very briefly talk to you about symmetries in materials. If we take as parameters the components of the crystal momentum K that I mentioned back in the band theory slide, then under time reversal, if we reverse the arrow of time, then K goes to minus K because velocities get reversed. Also, because the Berry curvature is like a magnetic field, it transforms in the following way. And if we have time reversal symmetry, then it means that the Berry curvature is odd in K. And to get the Chern number, we integrate over all of our space. And if we do that for an odd function in K, then the Chern number is equal to 0. What this tells us is that to get a non-zero Chern number and to have non-trivial topology, we need to break time reversal symmetry. And also it implies that we don't actually need to have a magnetic field, as in the case of the integer quantum Hall effect I mentioned back in my third slide, in order to have non-trivial topology. And this is what Haldane did with his model of graphene, which is the revolutionary material that you might have heard of, which is indeed a topological material. So he first approximated graphene with a tight binding approximation. That is, he considered only nearest neighbor hoppings, interactions. And he got this spectrum here, where the points like this one, that the conduction band and the valence band meet, are called Dirac cones. Then he opened these Dirac cones by introducing different on-site potentials. And finally, his ingenious addition to his model was to have an effective magnetic field where he included a Aharonov-Bohm type phase for next nearest neighbor hoppings, as if we have a local magnetic field, a local magnetic flux, but in such a way so that the net magnetic field is actually 0. So we actually don't need to have an external magnetic field here in order to have a non-trivial topology. Because solving for the model, we actually get a phase diagram here with a non-zero Chern number. And this was called the quantum anomalous Hall effect because it's the quantum Hall effect without any magnetic field. But then the question is, what is actually C not equal to 0? Why does that mean anything important? Well, if we take a material that has a non-zero Chern number and we put it, for example, in the vacuum which has a Chern number equal to 0, then something must happen, because Chern number equal to 0 is topologically distinct from Chern number equal to 1. And we said that through smooth deformations, you can't go from one Chern number to another in a continuous way. So something must happen at the edges that changes the value of the Chern number. And this thing that happens is the presence of edge states, which are thus topologically protected. And to see the importance of these states, for example, a characteristic of them is spin momentum locking. So these states live near the Dirac cones that I mentioned before. And if we take, for example, the cross-section kx equal to 0, we get these two lines. And we can see from the analysis that for one line the spins are down, and for the others the spins are up. And because the momentum is proportional to the slope of each line, also the momentums are in the opposite direction. So this suggests actually that the spin and momentum are locked. And this has huge applications in spintronics, for example. Now let's briefly bring back time reversal symmetry. So if we take two Haldane models with oppositely polarized spin, then for one of them, the edge state with spin up, for example, will move this way. But the other, which has spin down due to spin momentum locking, will move the other way around. But what happens here? Because we do have edge states here that are topologically protected, but we also have time reversal symmetry, because if we reverse time, then this gets mapped to this, and this gets mapped to this. So even if we have a zero Chern number, we still have edge states. Well, what happens here is that we have another topological invariant called the Z2 index, which also generalizes to 3D topological insulators that describe topological insulators in the presence of time reversal symmetry. We won't get more deeply into this, but we'll go to another kind of more modern type of material, which are the Weyl semimetals. So a question to ask here is, so the previous materials have had a gap, even though they were in a topologically non-trivial state. So question to ask, can we have a material with the gap closed but still have those edge states? Well, yeah. We need to be in 3 dimensions, and if we, for example, have an effective Hamiltonian near the Dirac cones like this one here, this is a 2x2 Hamiltonian for fermions with a specific chirality. And in physics, we know that these correspond to Weyl fermions. So we have 2 Weyl fermions closing the gap, or an even number of them, and they carry Berry curvature charge, which is associated with their chirality. So Weyl semimetals are actually 3D materials that have gapless spectrum with Weyl nodes closing the gap, and they're also described once again by the Chern number, but in a very interesting way. First, I'm going to tell you about the Nielsen-Inomiya theorem, which says that the chiral fermions in a lattice, it's very general, come in pairs of opposite chirality. So we always have them in pairs and an even number of them, which means that even if we include disorders just to get rid of them, it's much more difficult because we have to get rid of both of them, not just one of them. So they're more stable than the previous materials that I talked to you about. Just to understand some of their properties, we'll go through a famous model, which is the Burkhoff balance model, where they took a Z2 topological insulator that is in the presence of time reversal symmetry, and they stacked it interchangeably with normal insulators. While doing this, they got, of course, a 3D material, and the spectrum is the following. We get the 2 Weyl nodes that we talked about, but we also get a red line joining them. Don't forget that the Brillouin zone is periodic, so this line goes up to here and then continues down here. And then if we choose a 2D subsystem in real space, this corresponds to a 2D hypersurface in the K-space. And so if we choose, for example, this 2D surface, which cuts the red line there, the Chern number is non-zero, or here, for example. But if we choose it to be between the 2 Weyl nodes, then the Chern number is 0. But what happens here is that the Chern number changes. And we said before that when the Chern number changes, then something non-trivial happens. We have edge states. So we can see that just from that we have edge states where the Chern number changes. And this brings us to many interesting properties that Weyl semimetals have. One of them is the chiral anomaly, where if we apply a magnetic field along the direction of an electric field, then the electron density changes with time, and it's proportional to their inner product. This is a phenomenon from high energy physics mostly, and it's the first time that we see it in materials. Lastly, I'm going to talk about the nodal-aligned semimetals. So in Weyl semimetals, there's an even number of nodal points, even number of Weyl fermions. So this can be generalized to one-dimensional sources of Berry curvature, that is lines or loops or whatever. And depending on the path that we take in parameter space, then we pick up a different Berry phase. And this has many interesting applications. And these are state-of-the-art materials that have been only very recently been discovered. So closing, I just want to say that there are a lot more types of topological materials that I did not discuss about here, like topological crystalline insulators. The field is still on the rise. It doesn't seem to give up anytime soon. And it has many connections to high energy physics and many applications, because these edge states that I mentioned before are always protected by topology, which makes things very robust. Thank you.
Thank you.